Hey folks, today we're going to be talking about representing movement, and it's going to be the subject of two chapters in Robotic Systems, 8.4 as well as 16.1 through 2. So today we're going to be talking about how do we actually represent and reason about motions on a robot. We're also going to be talking about how robots actually physically execute motion commands that we may send to it, and also how do we program controllers that interact with robots to actually produce those commands. To start out, let's talk about representing movement. So we've seen how configuration tells us where the robot's pose is in its workspace. So we can think about the robot's pose as a point in a high-dimensional configuration space. So given a movement of that point in configuration space, we would see a tracing out of poses of the robot, which actually produces the robot motion. So there's a one-to-one correspondence between the actual robot moving and a curve in this configuration space. So we can try to model these curves in a multitude of different ways. Any kind of mathematical function that you can think of is potentially a way to create a valid curve as long as it maps to configuration space. There could be, for example, a straight line segment that goes between two points in configuration space. This is given by the standard interpolation formula. You could also include, for example, polynomials. It's also very popular to use piecewise polynomials, such as piecewise linear curves, as well as splines, such as the curved spline shown here. But in general, it can be almost anything. We're going to distinguish between a geometric path and a trajectory. By a path, we call a curve that's defined over some abstract domain, but the domain of the parameter is not necessarily that important. So the domain we can take, for example, to be 0 to 1, and the parameter is usually denoted by either s or u, and there's really no direct association between the derivative of this path and some sort of velocity or some sort of physical quantities. On the other hand, a trajectory is going to be a curve that's explicitly parameterized by time. So it's going to have a start time, an end time. These are going to be physically meaningful quantities, and the parameters are going to be denoted by the variable t, and the derivative will be the velocity of the path of the trajectory. So for example, we can denote evenly spaced in time by these little dots along the trajectory, denoting that this polygonal curve, this piecewise linear curve, can be executed by speeding up and slowing down at each of the vertices of the curve. Now, geometric paths versus time-parameterized trajectories are also important when we're talking about various quantities of these curves. So geometric properties will measure inherent shapes of these paths rather than taking any kind of parameterization effects into account. So for example, a geometric path will have a certain tangent, it'll have a curvature, and in 3 dimensions or higher, there are various other forms like torsion that you can calculate. Now, for a parameterized trajectory with timing, there's going to be the velocity, the first time derivative, the acceleration, which is the second time derivative, and higher time derivatives such as jerk, like the third time derivative. Now, we can also talk about various parameters of the properties of the curve itself. So there's the notion of parametric continuity, which is the standard form of continuity. So it's CK. For example, C0 curves are continuous. C1 curves have continuous first derivatives. C2 have continuous second derivatives, and so on. Now, there's also geometric continuity, which means that if we take the arc length parameterization of the path, then that path is CK continuous. The arc length parameterization is a mapping of points along the path such that they're evenly spaced in terms of distance traveled. So in other words, if you had some parameterization with the variable t, we could define some other parameter u such that if we take the path at that point, then the derivative along that path is going to have length 1. So as an example, for these two paths on the right, the first path is both C1 and G1, whereas the second path has a cusp in it, so it's not G1. But it could be C1 if the curve were to stop at the cusp. If you could imagine stopping at this cusp and then reversing direction, you could still have a continuous first derivative. All right, so these are important when we're actually executing motions in reality. So when we execute motions on a robot, they're going to be transmitted to some sort of motors or actuators. Very commonly, we use servo motors, which are high-gain, position-controlled or velocity-controlled motors. And basically what these do is if we tell it to go to a certain point, it will go to that point. Because these systems are stiff, they essentially have the dynamics being identity functions. If I tell it to go someplace, it will go to that place almost instantaneously. There are lots of caveats to that, though. If there's, for example, limited torque, so you can't instantaneously change direction. You'll have limited acceleration, velocity limits. There are also centrifugal forces and friction and so on that may cause you to not necessarily drive your robot exactly to the position where you want it to go. But if you have a high-performance servo, you'll basically be able to tell your robot exactly where to go and when to go there. Now, there are other types of robots that have various forms of different actuators, which, for example, have favorable properties like improving safety. So the series elastic actuators are one popular variant of this. They're featured on a variety of different robots. They're safer for humans to be around because they have a spring in line with the actual joint. And so there's the possibility of performing force control. You can also push on these and they'll act sort of like springs. However, they can't perform high-frequency motions. If you try to jerk one end of this, so basically if there's a drive component of these connected by a spring to the output component, and if you turn that drive component very quickly, it's going to be filtered through that spring to actually have lower frequency motion on the output shaft. So if we're trying to design motions and execute motions, we have to be aware of this type of behavior. Finally, there's also the notion of underactuation or compliance. So for example, if I have a multi-fingered hand, I may have only a tendon driving the compliance of a single finger, and the finger will wrap around an object when it makes contact. So in general, underactuation means that I have fewer control signals than degrees of freedom of my system. And these are characteristic of legged robots, multi-fingered hands, wheeled balancing robots, and so on. And so it's not even clear that a given motion that we plan can actually be executed on these robots. And so we have to be considerate of these factors when trying to design motions and execute them. The issue here is that actually the robot has some dynamics that are described by some differential equation, which are also known as the equations of motion. X dot, which means the time derivative of its state, is equal to some function of its current state and the controls that are given to it. So x here can typically be expressed by a pair of the configuration and the velocity of the robot. And the control is the input. So in the case of the servo motor, this will be its set point, where the servo motor is trying to get to. We often have fewer controls than we have state degrees of freedom. And in fact, for a motor, we only have n degrees of freedom and 2n state variables. The reason why is because the dynamics include inertia. This means that also it's said to be a second-order system. The robot is also affected by gravity, contact, and other external forces. So the motor controller, if you're going to take a course on control theory, you're going to design motor controllers that try to execute these controls as faithfully as possible. However, they can only do their best, and there's only so much that they can actually do. So, for example, PID control, proportional integral derivative control, is one way to try to control the x state so that it tracks a given set point, u, that you define from your command. So there's many different types of trajectories we could try to send to a robot in terms of the control command. One idea is just to send it the desired configuration that we want to go to. So this discontinuous mode of commanding is actually quite dangerous, especially for strong robots. You're going to reach dangerous speeds, and also you will overshoot your desired set point and potentially run into things. You could try setting higher rate discontinuous commands. But this will actually create your sort of effect of stutter stepping, lots of vibrations on your robot, and it's going to generally be a relatively unpleasant experience. Now, if you have, for example, a smooth trajectory, like a C0 continuous trajectory, a piecewise linear curve, for example, it may still have somewhat abrupt starts or stops, but you'll be doing better than before. And you'll tend to overshoot the stopping points. So as you stop, you'll end up overshooting and potentially running past where you want to go. Now, a better approach is to use a smooth curve, such as a C1 curve. And so here's a Hermite interpolation of the same milestones as before. Now you gain smooth transitions between each of the segments of this curve, but you do have higher acceleration during the curve. Now, the motor controller here is going to be responsible for figuring out how to respond to your commands. So if you were to have a very low quality controller, such as a PID controller, then you'll end up having to do a lot of this work on your own. But with more sophisticated robots, a motor controller is going to provide a lot of different types of functions. So for example, they'll perform interpolation and or smoothing so that the robot doesn't do this stuttering or have severe overshoots. And one example of this is corner blending for industrial robots that try to execute various curves. Another option for motor controllers is that rather than executing a whole motion, you can interrupt them. You can basically queue up motions, stop the motion at some point, and start to go to a different target. You can even interrupt in the middle of motion to start to deviate to a new target, and the motor controller can then smoothly interpolate for you. There's a couple of software libraries available for this. For example, Reflexes, Clamped also does this, but in any case, these are functions that may be available on your robot and they otherwise may not be. How these are implemented is that there's a motion cue that's stored on the robot, and at your current point in time, the certain positions and velocities of this curve will be sent to some low-level controller, the PID controller, which will work at a very high rate to try to execute those desired position and velocity commands. And they'll get sent to the actual motors. It'll be driving the robot. The robot will interact with its environment, and then it will get some feedback back into the controller. Now, as I move forward through time, I will start to just feed in slightly different positions and velocities to the PID controller, giving me a smooth motion. And as I move forward, this will generate a relatively smooth motion. And as an external controller, if I have a host computer, for example, I can start to tell the robot to go to a different future trajectory, basically by appending to this motion cue. And so I'll produce this suffix of this trajectory that will then allow my robot to continue on to some other desired target. Now, it's possible that you may also have functionality to interrupt or insert components of this motion cue. So for example, you could cut the motion cue at some point and deviate to a different path, and this will be really useful for responsive control. And the new path would look something like this, and then we continue marching along to the next point in time. Okay. Now, we also may have motor controllers that produce Cartesian paths. It's very convenient for a programmer to say, well, I want the hand now needs to move down at this given velocity. You may also want to move to a given Cartesian target and have this path interpolate between these in a smooth Cartesian motion. So the question is, how do we have the robot follow some sort of task space path when it actually only controls the motors? Now, really nice motor controllers will be able to do this very well for you. So the complexity here, though, is that when you're moving in joint control mode, then you can go in straight lines in joint control, and this will be very fast. This will be the fastest way of going between 2 points. But if you're trying to then trace out Cartesian paths, you'll no longer be moving in straight line paths in Cartesian space. So the figure here on the left shows a Cartesian motion where the blue segments are executed in straight line joint space paths, and the dotted orange segments are shown, those are Cartesian straight line paths. Now on the right, you see the corresponding joint space motions. So you see that the curved blue paths on the left are actually straight line paths on the right, straight line paths in configuration space. The orange paths on the left, although they're straight in Cartesian space, end up being curved when you look in joint space. So a motor controller that is able to do Cartesian path following actually generates these joint space paths dynamically for you, given your Cartesian commands. So for example, you may have a Cartesian velocity control functionality. If you have a desired task space velocity, xd, x dot d, what the motor controller will do is it will determine for each cycle the joint space velocity that it should attain to try to move along this, this Cartesian path. So this can be done, for example, through the Jacobian pseudo-inverse technique, such as the one found here. And then you can use this for the next velocity command. You'll then take the next Cartesian velocity command at the next time step, and then you'll continue doing this over time. There are a lot of caveats to implementing a really high quality Cartesian path follower. So for example, if you were to use this technique, you'd have integration error over time. Eventually you would go off of the Cartesian path that you're trying to follow, and then you need to actually correct for that during the operation. You may also run the robot into joint limits, and so the motor controller needs to do something, for example, stop the robot or issue an error when this occurs. There's also velocity limits, which get worse as the robot gets close to singularities. As the robot gets close to singularities, the amount of joint space movement that executes a certain task space movement grows with the condition number of the Jacobian matrix. And so dealing with these is a complex topic. It's oftentimes covered in robot control courses, but we won't have time to deal with it here. Now, the next question is, how do we then use a motor controller to then program the robot to do something interesting? And this is an issue of real-time programming. There's two general ways of producing real-time programs. The first is synchronous, and the second is asynchronous. In a synchronous form, you have a fixed operation that you do on a fixed time step. You input, you do some amount of processing, and then you output. So if you're going to be programming microcontrollers, or if you will be programming directly on an industrial robot control box, or if you're building low-level drivers on the host CPU that are operating at a very high rate, you'll be operating in synchronous mode. On the other hand, asynchronous mode is more flexible. You typically either use polling or event-driven control, and the different types of operations can be long-running in time. You also have less timing control, and so this becomes difficult when you're trying to work with high-rate feedback control, for example. Now, if we're going to be interacting with motion planners, if we have higher level controllers on the host CPU, or if we're dealing with user interaction, we're typically working in asynchronous fashion. So for a synchronous program, the general pseudocode is as follows. We're going to first set up a connection, and then we're going to start a loop. This loop is going to have a very fixed form. We're going to read the input, we're going to compute the response to the input, and then we're going to write the response to some communication channel. Finally, when we're done, we can shut down the communication. So all the stuff inside this block here, we're just going to call that process input. So basically, this is just a while loop. It's going to then process the input. I'm also going to show on these plots here, on the bottom here, going from left to right, we see time increasing. And so the signals, the communication signals from the device, like the motor controller, versus the processor, the device is going to be sending inputs to the processor. The processor is going to be doing some computation to compute the response that's indicated by those black lines, and then it's going to write the response back to the device. So now this is it's fairly easy to program synchronous nodes, but to do asynchronous nodes, we have to do something a little bit different. We typically don't have real-time operating systems when we're programming in Linux or Windows, and so we have to do some form of asynchronous programming. One very common way of doing this is known as polling. So polling means that we repeatedly check to see if input is available. If there's no input available, we just wait for some amount of time by doing a sleep. If there is input available, then we'll do some processing, and then we'll do whatever responses we'll communicate with our device as needed. So the timeline generally looks like this. The device will be idle at some points. The processor will start polling at regular intervals, sometimes not doing anything, but eventually it will find that a input has arrived from the device. It will then do its processing, and then it will spit the result back to the device. So here the processor is happening according to the demands of the device. And so you can see that the spacing between the processing is not even here. You can also handle multiple devices that you're communicating with at once. So for example, if you're reading from a camera and then writing to a motor controller, the device you're, for example, reading from device 1 is equal to the camera, device 2 is the motor controller, and then you can start to interleave these two together using a form of polling looking like this. So basically the while loop checks to see if input is available from one source. If so, it processes it. Otherwise, it checks to see if there's input available from a second source. If so, it processes it, etc., for however many devices you're connected to, and otherwise you're just going to sleep if there's no available input currently. There's some tricky bits about this. So for example, starvation of certain processes. If one device is sending inputs more frequently than the other, you have to be careful about not starving out the second device. But in any case, this is a reasonable way of programming asynchronous nodes. Another thing that you may want to do is have the asynchronous node do variable length tasks itself. So one very common pattern is to have some sort of manager that is dealing with high-level decisions such as user input or long-range tasks that are completed over the span of seconds. And then there may be a planner which may take on the order of half a second or part of a second to maybe a couple of seconds. And you can't tell necessarily how long that planner is going to take. And so then that planner has to communicate with some controller, which is operating at a high rate. So what typically will happen is that the manager will send some request to the planner will spend some amount of time, and then once it's done, it will then send its result to the controller, such as the path tracking controller, to then execute. Now, what happens when the input starts coming too quickly? So let's say that the manager makes a request before the planning is done. So there's two general ways to handle this. The first one is by using queuing. The way that this works is that we have some sort of thread on the planner, which is just reading input, and then if it gets input, it just puts it onto a queue. And so at this point in time, the planner will have two requests on the queue, and the code for processing this actually checks to see if the queue is empty. If there's anything in the queue, it will pop something off the queue and process it. Otherwise, it will do the sleep. So basically, in this timeline, the planner will address request 1. It will wait till the request is done. It will send that to the controller, and then it will start to process the second request. Another possibility is to use explicit signaling. So the planner can indicate to the manager when it's done, so that after it processes the input, it not only outputs to the controller, but it also reports done back to the manager. And the manager, by convention, is supposed to respect the status of the planner. So this takes a little bit more coordination between your different nodes, but it is also a valid way of handling these varying length tasks. As our controllers get more complex, it becomes important to diagram them in a variety of ways. We'll talk about two of them here. The first is called the control flow diagram. These were initially developed in the electrical engineering field to help design controllers of analog electrical signals, but we can also apply them to digital signals. Each block in this diagram is going to do some processing of the signal, whether it's a mathematical transform or some sort of computational transform. But what's important is that these are happening continuously over time. The entire diagram is essentially firing all at once, and each of the blocks does some processing of its input and outputs it to the next block. And the whole thing occurs every time step. You can think of it that way. So these blocks either process signals, they can output to the physical world, they can input to the physical world. They can also be used to input from higher level controllers. These can also be synchronous or asynchronous inputs from those controllers. Now, this doesn't tell us all the complexity that we need, and in fact there are lots of things that we need to do that can't be adequately expressed using a control flow diagram, and for those we'll oftentimes use state machine diagrams. So because control flow diagrams assume that each component has a fixed history-independent function, we can't necessarily express a lot of operations in this form. So although we might, for example, have a pick-and-place action that is a fixed history-independent function, that anytime we call it, it will do it, it's really taking several seconds to accomplish, and so we actually want to break this into several different components in sequence. So the way that our behavior is going to change depends on the history of where it's been before. So for example, in this case, we're going to, for example, wait for the object detector to complete. We will then initiate the grasp planner. We'll wait for the grasp planner to complete, etc. So we actually have stateful components here. So the state machine diagram tells us how these modes will then switch between these and based off of what signals. And so the general details are that each node here is going to be a discrete state of the process, or a mode. One of these is going to be designated as the start mode. Each arc is going to be some sort of signal that changes the current mode, and then each of these activates a certain mode-specific control flow when it's activated. So as an example, we have, for example, error handling. This is a very important use case for state machines. So if a component is reporting a fault, we'll oftentimes want to change to a different mode where we're not doing more stuff that could further damage the system. Otherwise, errors are going to just grind everything to a halt. Things are going to expect inputs are going to be there, but they're not, etc. And so we do need to have error handling, and state machines are a great way to do that. How do we actually program something like a state machine? Well, the loop looks something like this. So this is a very simplified version of this with just a single Python function and some global variables denoting the state, although you will probably want to put these into some sort of class. So you'll maintain the state. Here, everything is going to be, all the states are going to be denoted by strings. There's going to be, for example, the time that you enter a state that you'll maintain. There will be some data that you may maintain as well. And so what you'll do in your control loop is that you'll read from your sensors, which could also be, for example, the clock, as well as the joint encoders of your robot. And depending on what state you're currently in, you'll do some processing for that state. You may, for example, have a time-dependent exiting condition. And so here from lines 10 through 12, it will check to see whether you've been in this initialization state for a second, and if so, it'll move to state 1. And then it will change the time at which you enter state 1, etc. So there's an incredible richness and complexity of the types of behaviors that we can implement through controllers. But today, when we've talked about motion representation and execution, we've talked about the variety of different motion representations that are available. We talked about the discrepancy between geometric paths versus time parameterized trajectories. We've also talked about how to execute motions using control loops. And in particular, these motor controllers may implement functions like motion queuing and Cartesian control. To then integrate with those motion controllers, we can use various forms of control flow diagrams and state machines and programming practices to interact with those motion controllers. That's it for today. I'll see you next time.